Okay, and the last time we looked at addition, and we can quickly review it with these questions. The first one, we said compute 3 plus 13 plus 23 plus 33 plus 43, and that one. So, and from the last class, we mentioned that for us to do this easily, we had them systematically. And how do we do that? We realize that the last one here, which is 43, if we add it to 7 here, it will give us 50. 33, add it to 17 here, it will give us what? 50. The same thing 23 and 27. So it means we get the same thing with 3 and 43. So it means for this group we get 50. For the second group we have 50. For the third group we also have 50. And for the fourth group we have 50. For the fifth we have 50. So with that, it means we are adding 5 copies of 50, which is 5 times 50, and that should give us 250. You can see how easy we have done that. So you should be able to compute the second one too. So from there, you can see from here we have seen the concept multiplication. When we have 5 copies of 50, instead of adding 50 plus 50 plus 50 plus 50 plus 50, we said 5 times 50, because we have 5 copies of 50. So it means multiplication, whenever we talk about it, it means same copies. When we have same copies, so it means you may also have 30 plus 30 plus 30 plus 30 plus 30. How many copies of 30? 5 copies. And that is 5 times 30, which is 150. So that is the concept of multiplication. Now, let's move a little bit ahead. Okay, so in this case, we have multiplication. We have, using the picture below, explain that multiplication is also commutative, like we did for addition. So in this case, 2 times 3 is equals to 3 times 2. We want to use this picture. When you look at this picture, this is figure A, figure B. So what do you see? Any difference there? In figure A, we have, you can see that we have 2 rows. We call this row 1. This is row 2. Okay, so it means you have 2 rows. But for every row, it has what? 3 squares. Every row has 3 squares. This is square 1, square 2, square 3. So it means in this case we have for each row 3 squares. So can we count everything all together? It means we have 3 multiplied by 2, or 2 rows by 3. So it means in this case we say we have 2 rows multiplied by 3, and that is what we have here. So multiplication is also counting, but we are counting same copies. Same copies. When I know that every row has 3 squares, so I don't need to go to the second row to count again. I already know that it is the same copy of row 1 that we have in row 2. So what do? I say 2 multiplied by 3, and that is what we have done here. Then when you come to this second figure, figure B, we have 3 rows. Row 1, row 2, row 3. And in that case, for each row, we have what? 2 squares. So, and there are same copies in each row. So in that case, we rather say, instead of counting everything, we rather count as 3 multiplied by 2, because you have 3 rows multiplied by 2 square per each row. So you realize that these two are the same when you count. The only difference is that figure A has been turned to become figure B. When you turn this, it's either you turn it in a clockwise manner, you turn it like this, or you turn in an anti-clockwise manner. It means it will still give you figure B. So meaning that when you turning an object does not change the counting. Or flipping, Okay, sorry, this is not it's still the same thing as flipping, because it's still this that is coming to this, and this is coming to this. So just like in the case of addition, when we flip, it doesn't change. And this concept is known as commutative property of multiplication. So in that case, we say A multiplied by B equals to B multiplied by A. That is in algebra, in a way of generalizing that. So that is the concept. Let's see whether the concept of associativity is also will also be obeyed in this case. Okay, so by counting the dots in the picture below in different ways, explain 2 times 3 times 4 equals to 2 times 3 times 4. You can see that they are the same number, 2, 3, and 4, 2, 3, and 4. But we are doing it in different manner. The order in which we are multiplying is different. So the first one here, we are multiplying 2 and 3 first before you multiply the result by 4. The second one, we are multiplying 3 and 4 first before we multiply the result by 2. So now, in the same way, when you look at this figure, in what way can you count it systematically? One way you can do that is, okay, we have 2 rows, row 1, row 2, and for each row, what do we have? For each row, we have 3 squares. Square 1, square 1, square 2, square 3. So it means I can easily say, just like we did in the commutative property, I can say 2 rows by 3 columns. So 2 times 3. Then I now realize that for each square, 2 times 3 will give us the number of squares we have. How many squares? 1, 2, 3, 4, 5, 6. So 2 times 3 will give us that. But then we also realize that, inside each square, we have 4 dots. So to get that, it means the total number of squares multiplied by 4 will give us the number of dots we have, which is 6 times 4, and that is 24. That's one way of counting it. Another way of counting it is to say, no, okay, don't let us do it that way. The way we can do it is that in every row, let's count the number of dots. We have seen that we have 3 in a row, we have 3 squares. In a row, we have what? 3 squares. So let's count how many dots do we have in a row before we can multiply it by 2. You get it? Now, so in that case, we say we want to know the number of dots in a row. In a row, we have 3 squares, and that is why we have 3. Multiply by, in every square, what do we have? We have 4 dots. So this is that. Then we can now say, let's multiply it. This is what we have in a row. In a row. And we have how many rows? We have 2 rows. So to get the number of dots in everything, we say 2 multiplied by the dot in a row. That's 2 times 3 times 4. So it means with that, we can say that these are the 2 different ways with which you can count that systematically. So it means it's telling us that whether we do the first one, which is counting the number of squares first before multiplying by the dots, or doing it in the other way, we still arrive at the same result. And that is telling us that multiplication is also what? Associative. It's associative, and in that case, in algebra, we say A times B multiplied by C equals A times B times C, in this manner. So that is associativity. All right. So it means that in both in multiplication, we can also see that what commutative rule property is obeyed, and likewise the associative property is also obeyed. So based on that, we can also generalize that any other rule, as in the case of addition, also hold in what? In multiplication. So can we use that to compute this? 25 times 1, 25 times 4 times 6 times 8. Now, computing this directly like this, it will be very tedious for us. We need to do it systematically. And that is the reason why we need any other property. All right. So what do we do here? We know that 25 times 4 will give us something very okay, and that is 100. The same thing, if that should give us 100, then what of this? You know that too. So it means, and that one will give us what? 1000. It will give us 1000. So you can try that. Those are some of the things that you should know quickly. At least you should be able to bring those ones out quickly. 25 times 4 will give us 100. 125 times 8 will give us 1000. So in that case, it means when you arrange them in that manner, we can say 25 times 4 multiply by 125 times 8, okay, multiply by 6. So we have 100 here, we have 1000 here, and we have 6 here. 100 times 1000 is 100,000, multiply by 6, that's 600,000. You can see how easy it is. So that is the approach we would like us to be using. Can we also look at this, compute this? Don't forget, when we are computing, we must apply the BODMAS, the bracket first. So in this case, when you see bracket, that's the first thing you attend to. Okay, look at this. You can also see that, is this similar to associative property? Let's see. From associative property, we know we have done for addition. It means all the sign must be addition, must be plus. We have done for multiplication, all the sign must also be multiplication. But does it hold when you have different sign? That is what we want to establish here. Does it hold when we have different sign? So this, when you apply the BODMAS, we have 5 plus 6 is 11 multiplied by 7, which is 77. So can we apply it here? 5 plus, the first thing we are going to multiply, we are going to deal with is the one in the parentheses. 6 times 7 is 42. So when you add them together, that is 47. So you can see 47 is not equal to 77. So it means this does not hold. It does not hold. So 5 plus 6 times 7 is not equal to 5 plus 6 times 7. So it does not hold. It must be the same operation before it can hold. All right, so let's see this. This is also another concept. Let's see. We can see that does not hold for different sign. But do we have something of this nature? Look at what we have done here. 2 multiplied by 3 plus 4. Is it the same thing as 2 times 3 plus 2 times 4? So you can say this is not actually associative, but this is also one of the properties we talk of, which we usually call distributive property. So in our next video, we are going to cover that. What do we mean by distributive property? How do we use them? And can we have them? How do we write them in algebra? So thank you very much for listening. Do watch out for our next video.